So onward, we're going in chapter 2. And the book chapters are long, so it's nice to have a break. And I try to pick the break at a point where we kind of have finished talking about a subject, and then we move on to a slightly different subject. They're obviously related. So we did our first part of our lecture today about the excavation, right? How do we get the hole to build the foundation? And then we're going to move from there into types of foundations, right, and how foundations work, which will then segue into next class when we start talking about concrete, which is what we build foundations out of. So hopefully that makes some intuitive sense. So when we start talking about foundations, we can break a building down into several distinct parts, okay? We have the superstructure, right, which is the stuff that's above ground, right? It's everything that we can see about a building. So it would be everything that we're inhabiting, right, that sort of thing. The substructure would be if the building has any basement floors or any lower levels, right? And then below that, we have what's called the foundation, right, which is a lot of times what we're building the excavation for in the first place, or which is where we're going to start. The bottom of the excavation is where we're going to start the foundation, right? So factors that determine foundation type. What would you think would be the key factors that might determine what type of foundation you would have? Right? We've already talked a little bit about it. Yeah. Weight of the building. Sure. Absolutely. What else? Soil type. Okay, I heard a variety of soil type mumblings from people, so I'm not picking anybody in particular. Anything else? Right? Seismic loads that might be on a building. Right? It's kind of wind loads. Right? These are kind of all the things that we talked about. Right? Before. Right? So we've got primary factors. Right? Subsurface soil and groundwater conditions, right? Structural requirements for the building, right? Which are all the things that you guys talked about, okay? The secondary factors, right, are things like the construction methods. What kind of access do we have to the site? What kinds of equipment can we bring to the site? Those kinds of things. What kind of environmental factors, right? Noise, traffic, disposal of whatever we're excavating, right? Those kinds of things. Proximity to an adjacent property, right? Which we'll talk. We have some specific examples of foundations near adjacent properties. What kind of building codes or regulations might be there? What kind of time would be available for the construction process, right? How long can it take us to build the foundation in the first place? And what kind of risks might be involved, right, in making it, right? So we'll start with what are called shallow foundations, right? These foundations are generally simply footings, right? What we would call footings. Right? And so this is on the scale of a residential house usually, right? Maybe a slightly larger building than that, right? And so we'll start with the most simple type of a footing, right? Which is a basic column footing, right? And so the idea here is it's like we're standing, right? If you were all standing right now, you stand on your feet, right? There's a reason we call this a footing, right? It's what the column or the wall stands on, okay? So we have a square block of concrete that's underneath, right, the column. And basically what it does is it accepts a concentrated load from the building, right? We had all those load factors, the dead load, the live load, the wind loads, right? The snow and the rain, all that stuff, right, is coming down or up in some cases, right, through this column, right? It's a very concentrated load because we're taking that load from the building itself, right, and we're pulling it all into this one column and we're putting that weight on the ground, right? What the footing does is it spreads that weight out, right, so that the weight, right, when it comes in contact with the soil, doesn't exceed the maximum amount of weight that the soil can hold, right? So we spread out this block. We make this block large enough, right, so that the soil can then support the amount of weight we have coming down on the column. Make sense? Right? So this is the most simple type, right? I'll show you a variety of these things, and I'll give you a little bit of time to draw these out. Okay. Likewise, I'm going to show you when we first start drawing kind of what I'm after in terms of drawing. I don't expect your drawings to look like Francis Chain's drawings, right? That's perfectly okay, right? But these kinds of things can help you a lot in terms of understanding and really learning the material, which is why I'm going to make you draw and label things, right? Because that process will help you retain it in your memory, okay? So when we talk about a base footing, right, and these have a little bit more detail, okay, what I'm going to ask you to draw, and I'm going to flip on the lights. This projector, they replaced it last year, and I think it's decent enough to where you can still kind of see it with the lights on, right? Okay? So we'll be flipping on and off, right? But the idea here is you don't have to draw both of these, right? You can pick one or the other, but it's a good way of identifying what this is, okay? So the idea is that we have a footing, right, that's underneath, right? We've cut through a wall, something like this, right? And depending on which one you're drawing, I'm going to draw the one on the right for lack of something better, right? We have the column, right? It's got a little bit of a cap here that goes like this, right? There's our column, right? Come along here, draw this out, right? Something like that. And what we're going to do, right, if I can draw it correctly, right, is we're going to put a few labels on this. We'll call this a footing, right? We'll call this a column, right? And it doesn't really say this, but we'll call this a floor or a slab, right? Does that make sense? Right? And so in something like this, you might also make a few notes that says, you know, column has concentrated load from building, right? Column has concentrated load from building, right? Footing distributes load to allowable soil pressure. Okay. Most of the time I won't write out the notes, but since we're just getting started, I want you guys to kind of see the types of things that I'm asking for. Does this make sense? Right? Basic labels, a few notes of what's happening, right? And so we're translating something like this, right, into your sketchbook. Make sense? Yeah? Okay, so I'm going to give you a little bit of time to draw it, right? And I have to kind of learn how fast you guys draw and that sort of thing because it's going to vary a little bit in class, okay? Remember, when I look at your sketchbooks, I am in no way grading on how well you draw. They can be just little scribbles. It's perfectly fine. These are designed to be helpful for you when you're going back to study, right? They're designed to solidify the things we're talking about, right, in your minds, right? Which is why the labels are really good things to have, right? All right. You can ignore this bean pocket thing, right? It's a note for something else. So while you're continuing to draw this, I'm going to just make a couple notes about things that are happening here because it's always helpful when you're kind of seeing how things go together, right? On each of these, we have the column coming down, resting on the footing, right? But in each of these cases, right, we have a different material that is the column resting on the concrete footing. So in this case, we have a steel column that's coming down, resting on the footing. In this case, we have a wooden post or a wooden column coming down and resting on the footing, okay? In this particular case, we're embedding the steel all the way down to the footing. We're using 2 anchor bolts to anchor that column to the footing itself, right? These little anchor bolts would be embedded in the concrete when it was poured, and then the column would be added later. There's a bit of an expansion joint, and then this is filled inside with a grout, or basically concrete, to make up the floor, right? Which we'll talk about all these in depth, but I'm just pointing it out because we're here and you're drawing anyway, right? In this particular example, right, we have basically a little concrete pad that accepts the column, right? It holds the column in place. There's also a steel rod that runs up inside to tie the two together. A little bit more of an old-fashioned way of doing it. If we were doing this today, there'd probably be a steel bracket on the bottom with bolts that would bolt through, right? So things change a little bit. This concrete pad is held up a little bit higher than the surface of the floor as well, right? So I'm just pointing out a few notes. Those aren't critical, but it's nice and helpful certainly to get those notes. You guys ready to move on, or you need a little more time? Seeing how many people are still writing or drawing. Right? Okay, so we'll move. There'll be more opportunities, right? Okay, so let's turn this back off again, right? Footing size. I'm not going to ask you to calculate how big a footing would be, right? This is too much information. It's for more of a structural class, right? Which you're, of course, going to take at some point. If you move on and say you're at Berkeley, you're going to end up taking one of those classes. If you go to Cal Poly, you're going to take one, that kind of thing. But the idea here, right, is that we're going to have a variety of factors that are going to allow us to calculate based on how concentrated our point load is and how much width we need in our footing based on what the load is and the bearing capacity of the soil. Right? You can look those up later if you want. Okay? So we move from a column footing into a wall footing, right? Which is basically exactly the same thing, except that now instead of coming down as a point load, right, we're coming down as a linear load, right? So this is now, right, we can imagine this, right, as a little column, right, but we're extruding that column back so it becomes a wall, right? Same basic idea, right? It's a continuous strip of concrete that serves the same function, right, as the column footing, right? It's distributing the load that would be resting on that wall, right, to an allowable size that the soil can bear. Does that make sense? Yeah? Okay? The footing needs to be large enough to spread out the weight from the wall, right, not to exceed the allowable bearing stress of the soil. Okay? So if we were actually pouring this kind of a footing, it would look something like this, right? And we'll see a bunch more of these examples when we get a little bit further down the road in concrete, etc. Since we've been talking about dewatering, I'd like to point out how much water is in here, right? Which is a bit of a concern if I were doing this building, because this water can have a tendency to separate out the concrete, which gives you a lesser strength of concrete, which could compromise the foundation long term, and that sort of thing. So we'll point that out later. Notice also, this is not one of my jobs, right? Notice how much concrete they've spilled in this process. I mean, it's just, this is not the best example ever, but you get the idea. It's showing you footings, right? So the idea is that we then be building the footings, right, on top, or building the walls on top of those footings, okay? So moving from, right, column footings, wall footings, now we're going to talk about what's called a slab on grade, okay, which is exactly what we're standing on here, okay? A slab on grade can only be used when there is little or no ground frost, okay? So we would not want to make a slab in, say, Alaska, right? Bad idea. The ground freezes, right, which can cause things to happen, okay? If we're here, yes, you're all saying, but wait a minute, it's been really, really cold lately, right? Yes, it has been really cold for our standards of being California people, right? But if you talk to somebody back east, they would say, oh my God, it was 32 degrees for you guys? That's like warm. That's fantastic. What are you talking about? I'd kill for a day like that, right? So our definition is a little bit skewed as California people, right? But a slab on grade is a great solution for California climate, right? It's very reasonable. Very reasonable down in Arizona, right? Those kinds of climates, okay? So it's the least expensive type of foundation because it doesn't involve too much digging, right? Too much excavation, which is great. And it can support 1- and 2-story buildings, right? So we're here, we're in a 1-story building, works out great, okay? And so it looks roughly like the one we're seeing on the right there. These are some of the details. This is a quick draw in your sketchbook. Shouldn't take you too long to do something like this. So since it's the first day, I'm drawing with you, right? So we'll get rid of this one. We'll talk about the slab on grade a little bit. Sometimes the process of drawing, right, helps you to kind of learn what's going on in the picture too, right? Certainly if you've taken architecture classes, you've seen these kinds of sections and stuff before, but at least now maybe it's going to sink in a little bit better. If you're not used to seeing this, maybe by talking through it, it can really help us out, right? So in this particular example, right, we start with, right, our slab. It looks something like this. When we get to the corner or the edge of the slab, right, the slab is going to turn down, right, and kind of have a little bit of a built-in footing, something that looks like that, right, which allows us to have, right, the outside dirt, right, and what would be underneath the slab itself. We'll put a little break line in there, right. On top of this slab on the corner would be your wall, right, Right now, in an image like this, it's a very generic wall. We're not talking about what the framing would look like. By the end of the class, you'll be able to draw from the foundation of a building all the way up through the building, right? Depending on how it's built, right? So we'll talk through that. But for now, it's fine. It's just a simple wall, right? If I were drawing this, right, I would make a note that this is a slab on grade. Right? This dotted line here is representing a piece of rebar that's in the slab. Also, these two dark circles are also representing pieces of rebar. We'll talk about what rebar is long term, but for the sake of your drawing, go ahead and draw these pieces in, right? And put a little label on them that says rebar. Like that, right? If you want, you could put the hatch, right, for concrete in here, if you want to be technical about it, right? Something like that. Make sense? Right? You could say this is dirt, right? Or outside. Right? You could say this is inside. Right? Labels are great. Make sense so far? Okay. So onward we go. Okay? I'm not asking you to draw each one, right? I picked the generic one, right? But I at least want to talk through some other things that do happen in a slab on grade, and we will cover slab on grade in more depth in a couple lectures. Okay? So in this particular example here, right, we have our slab, but we have a piece of rigid insulation, right, that's separating the slab and the interior from the exterior, which is part of what we're doing for environmental reasons, right, heating and cooling of the building, that sort of thing. Right. In this particular example, we have a bit more of a foundation stem wall with a slab on grade still, so it's a combination. And so we'll talk about those in a little more depth. Another example here, right, where we have an exterior masonry wall coming down to rest on a footing with an interior slab that's separate and apart from, right, but that's still providing the floor of the building itself, right? So we'll talk more about this stuff later on. These are just general conceptual ideas. Right? We'll spend much more time on a slab on grade. Okay? So, how many people have a slab on grade house or know if they have a slab on grade house? Okay? Good. Okay? How many people know if they have a crawl space? Right? My house has a crawl space. Right? How many people have actually been in their crawl space? Right? That's good. That's good. Right? So, crawl space is very, very typical for this area, for our type of construction, right? Residential. It's supposed to provide 18 inches or more of space to crawl around under your house, right? The reason it's called a crawl space is because you can't stand up in there. You actually have to crawl around, right? Now, it's supposed to be 18 inches, right? My house is maybe 12, right, if I'm lucky. So if I'm crawling around under there, it's a very challenging experience, right? Some of the projects that I've worked on, actually, they have a pier and grade beam system, and they have as much as 4 feet underneath, right, depending on the slope of the house and what have you. So it's almost a basement that you can kind of use to store things if you had access from the outside, which you don't, right? So it's going to vary a little bit, but the idea is that you can crawl around in here, okay? The floor is then raised off the ground, right? So it's not going to be a slab on grade anymore. Chances are it's going to be some kind of wood frame construction, right? The nice thing for this is it can actually allow for better insulation of your building, right? So this is the bad example at my house because there is no insulation underneath, right? It was built in the 50s, kind of your classic uninsulated house, right? But if you're building a new house today and you have a crawl space, you have the opportunity to put insulation in that floor, right, which creates a nice insulated envelope for you to live inside, right? If we're standing on something like this, right, this doesn't have any insulation. We're using the ground, right? This is a slab on grade. We're using the ground as insulation, right? But it's not quite as good as if we actually had insulation in there. Okay? So this one is also a little bit more complicated, but we want to kind of illustrate this out a little bit, right? So concentrate, ignore this stuff here, right? We're just drawing this condition right here. Okay, so in this particular condition, we're going to talk about the crawl space, right? So we have, right, our foundation wall that's coming down. We have our footing at the bottom, something like that, right? On top of the wall, right? And we'll talk when we get to the wood construction part about the details of this construction. But basically, we have what's called a mud sill there, followed by our floor joist here, right? Which is enough for you to just label floor, right? Down here, right? There's our soil outside the building, right? Our soil's going here, right? We'll label this as outside, right? We'll label this as inside. Right, let's give ourselves some break lines. Right, we can break this too. Right, this would be our crawl space. Right, make sense? Right, these other examples have to do with how you're framing out and what kinds of supports you have inside the building. When we get to the wood frame construction part, this stuff will be far more important, and you will completely understand what's going on. But I'm not asking you to memorize this stuff or think about this stuff now. Okay? Just a different example of a perimeter grade beam, which really isn't relevant yet because we haven't talked about it. Okay? Okay. So the third option, right? We started with slab on grade, then we moved to crawl space, would be to actually have a full basement. Okay? How many people have a full basement? Okay? Much more, there's a handful of you, much more uncommon in this area. If we were back east, it'd be very common, right? And so depending on the geography and the geology of the place, it's going to be more or less common, okay? It's an extra amount of living space that's at or below grade, right? Or partially below grade, okay? The thing about it is you have to be very careful in how, right, you deal with the waterproofing, right? Because if you have any water outside, it can get into this hole, right, which is problematic. So you have to be careful there, right? It certainly requires more excavation and is consequently more expensive to build, right? Which is, if we go backwards to the slab on grade, there's almost no excavation, cheaper to build, right? So we have to pay some attention to the structural loading, right, which I'm going to walk you through, right? I'm not asking you to draw this out, but I want you to have some idea of what I'm talking about here, right? So previously, we talked primarily about weight coming down, resting on the foundation, distributing that load, right, into the footing down here. Make sense? Right? But in the case of a basement, right, we have a hole on this side, right, we have dirt on this side, and we have pressure causing, right, there to be lateral force on this wall, right? So just like we talked about with the excavations, we have to deal with how do we support that kind of, right, pressure that's on the wall. It depends on how deep the basement is, and there's a variety of strategies. But it's important to recognize those types of loading on the building. Every one of these little arrows, right, is representing load and how much load, right? So we've got a bunch of little arrows here that get distributed along this beam. That then comes back with a lot of weight coming down here, right, and a lot of weight coming down here. Then we have little arrows pushing down, little arrows pushing up, right, from pressure coming up, right? Small arrow getting to big arrow because more pressure is at the bottom, depending on how deep you go. Right? So that's how you're supposed to read this kind of a diagram, right? If we were in structures class, you'd be able to calculate all that, right? That's why they make you take calculus in the first place, right? Those of you that have taken calculus, right, should recognize these kinds of shapes, right, and being able to calculate load and that sort of thing, right? Right. Thankfully, it's been a really long time for me, right? Okay, so what about if we're on a hillside? Okay, we've talked about flat lot conditions, which are relatively simple to understand. If we have footing on a hillside, right, that footing needs to maintain a required depth, right? So what we have to do is we have to step that footing down, right? And so if we remember back to that picture that I showed you with the weird water when they were pouring the concrete, there was actually a stepped footing there, right, where it was coming down, okay? So the other option, right, especially if we have earthquake zone, right, so when you're thinking this kind of a foundation, you should be thinking like the Oakland Hills, right, that kind of an area, right? In an earthquake zone, right, we're going to have column footings, right? So we have these really deep footings, right? And then we tie them together, right, with beams that run along the surface of the ground, right? So we're creating a far more complicated mesh of a foundation, right? And this can work in flatlands too, right? So we have these beams that tie together between the column footings that are running down. Make sense? Yeah. Right. So we don't have a footing, right, that goes right all the way down or steps down here, right? We're relying on these column footings, right, which are very long. They're almost like piles, right, where we've driven these down in and we're tying them together with a grade beam on the surface of the ground, right? So instead of having to do all that excavation, we're just drilling really deep holes and we're tying all those together. Right. This is separate from this, which is separate from this. Here. From here? I'm just trying to make sure I'm understanding. This beam, this one is the same beam. No. Oh, this here, right? Column. You were throwing me off with beam. Sorry, I'm getting confused. It's okay, no problem. Okay. So you're saying, is this a continuous piece, right? It can be, but it doesn't have to be, right? This with this is far more important, right? In this particular drawing, it's showing this as concrete, right? But this could actually be framed out in wood. Okay, so it's not necessary that that piece of it be concrete, right? The drawing in the book happens to show it as concrete, right? The important part is everything that's actually below this line, right? And it's one of these unfortunate things where, I love the book and it's a great book and it covers everything really, really well, but a drawing like this I don't think is clear enough, right? They need like a 3D representation of this because it just doesn't show as well as I would like it to show, right? So this one's a little bit simpler because they've removed the top part of it, right? But this is very much the same concept, right? And what this is it's this reinforced concrete beam, right, that runs along the surface, right, where we have these, right, piers that go down into the ground, right, and then this ties it together. But we've removed that upper portion, right, so that it simplifies it a little bit, okay? So in this case, right, load that comes down, right, ends up putting pressure on this beam, which then redistributes the load out to the various piers, okay? And we'll talk about pile caps and caissons a little bit better. The other thing that I don't particularly like about the book is that the only place it shows you the grade beam is on the slope, right? A lot of times grade beams are on flat ground, right? And they're used specifically in California in this area, right, for foundations with high movability. So if we were in expansion and contraction, right, if we were in a clay soil area, right, this type of foundation is perfect, right? And so I'll try to go off on a tangent and talk more about that and why you would want to use it in a little bit, okay? So I apologize that those are a little confusing, but I'm stuck with what the book has to say, okay? So in this example here, we have what's called a stepped footing, right, which we talked about before, where you see the footing actually steps back, right? A little bit clearer. See, we're in Francis Ching realm now, so the drawing's actually clear, right? It's like they need to communicate and have Francis do the, drawings for the book or something, right? So we have this, right? These are footings on sloping ground, right? In this case, they're more of a column footing, right, where we have a footing and a footing. They're going up to attach to something up above, right? But you get the idea. Right? Oh, I'm asking you to draw these in your book. You don't really have to draw these. It's okay. You've drawn a bunch, right? Okay. So what about if you're in San Francisco and you have one of the Victorians that are sandwiched one to the next, right? So when we talked about a column footing, right, we talked about the footing or the column coming down and then the footing distributing the load out in a square around that column. Okay? If we didn't do that, then let me take a second and draw this in a little bit, because this might help. You don't have to draw this, but I'm going to try to draw to illustrate a little bit better. Okay, so we're going to draw this in section, right? There's my footing, okay? My property line and my building, right, we'll call them right here, okay? Ideally, right, I would come down right here with my column, right? I'd have nice footing on either side of the column, right? Weight would be good, okay? Problem is, my property line is right here, okay? I can't build a footing over here because I don't own this piece of property, right? That's my neighbor. So now we have a problem, right? So I can't have this part of the footing. Okay, so we get rid of that part of the footing. Use something, right? So, okay, well, to compensate, because I still need the same area, right, to support the weight, so I'll make the footing a little bit larger over here. Okay, so that's good. Theoretically, it can support the weight. Okay, but there's a problem, right? I have all the weight coming down on this corner of my footing. Okay, what's going to happen over here? Right? This is going to lift right up. Okay, so that's problematic, right? So when I have a condition on a property line, I have to be very careful about how I design the footing, right? So this is one solution, right, where I have the column, right? This could be a wall. It doesn't really matter, right? I have the column coming down, right? It's resting right on that edge. In order for the footing not to overturn, right, I run it all the way back so I have another column coming down on it, right, which is then holding it down, right, which is not allowing it to overturn. Make sense? Right? So the point is, if I have that special condition, I have to change how I design the foundation. This makes it more work and more costly to build the building, right? So that's called a combined footing, the one on the right there, right? The other option that I have is called a cantilevered footing, right? Similar concept, right? But it's where I have the footing down below, I have a column coming up, then I have a beam that runs to the next, right, column and footing, right, which can then support the weight from up above. That make sense? This is way more costly to build, right? So we increase the cost every time we do something like this, right? So chances are you've driven down the streets of San Francisco and you've seen one of these, but you probably haven't thought, well, I wonder how they did the foundation, right? These are the kinds of things that a class like this is really important to think about, right? Because it's these things that you don't think about, right, when you're just driving down the street, okay? So we move from that into deep foundations, right? And we're moving from the realm of your residential construction into the realm of I'm going to build a skyscraper, right? These are much bigger types of construction, okay? So this diagram, right, is in the book. And the idea is that by the end of today, you would be able to fill in, right, what each of these bottoms looks like, right? And it's kind of unfair because you can see what this bottom looks like, right? So you got one right, right? Let's give these a shot. At least draw them in, right? See if you can come up with what they look like. Now, it's kind of unfair if you flip open the book and look at what it says. If you really don't know, right, just draw this, because the next slide is going to have the answer, right? This type of a question is a really great, and I'm not going to ask you on a test to actually draw these in, right? But the act of having to draw these in will solidify the differences between each, right? Because they're very distinct, right? So let's move. Anybody feel like they totally nailed it? No? Okay. Okay. So this is what they look like, right? First one is, so this is called a caisson, okay? Caisson here, it has a bell flare at the end, and we'll talk about what that does, right? The next example here is called a socketed caisson, right? It's coming down and actually going into, right, a nice solid subsurface material, right? We have what's called an end-bearing pile, right? Bearing weight where it's resting, right? And the last one, which you all got right, and I'm so proud of you for, right, is called a friction pile, right? And so we'll talk about what each of these mean in just a second, okay? But being able to kind of complete that diagram will make you really, it signifies that you understand what each of these are, okay? So, caissons. Caissons are drilled piers, right? They're similar to a column footing, right, in that it spreads the load of the column, or that's resting on it, into an adequate area of soil, Okay? And so we moved, just like I talked about, we moved from the residential, the small scale, into the big building scale, right? The bridges, the skyscrapers, that kind of scale. Okay? And so what happens is this caisson, right, the purpose of this caisson is to go through the poor soil that might be at the top until we get down to where there's an adequate supportive soil that we can actually rest the weight of our building on. Okay? So it's drilled, which is important. Okay? So these can be constructed by hand or by machine. Okay? Obviously, in this day and age, most of the time they're constructed by machine. Right? They're usually very large in size. Right? And so I'm showing you a picture like this to give you some idea of how large it is. Right? Often there's a belling or a flaring of the end of the hole. Right? So when you get down to the bottom, right, to increase, right, the surface area that this can bear weight on. Right? Remember, the soil can only bear a certain amount of weight. Right? So we flare out the end of this caisson to give us a little bit more surface area to bear. Right? The concrete is then poured into the hole, right, to fill it after the hole's been drilled, right, or dug. Right? Reinforcing is pretty rare in these. Right? The bulk of their purpose is to support the heavy load going down in a building rather than seismic load, right? But it varies a little bit, okay? So there isn't too much reinforcing. If there is any reinforcing, it tends to be toward the top, okay? The diameter is anywhere from 18 inches, right, which is relatively small, something you might see on a multifamily building or something like that, right, all the way up to 8+ feet, right? So they can get very large in size. Obviously, if we're supporting a skyscraper or we're supporting the Bay Bridge or something like that, right, much bigger pieces, okay? The thing about it is, because it has to be drilled, it can only be done in cohesive soil. So it can only be done in things like clay, right? Because if we were drilling in, say, sand, right, when we drill, it fills back in, right? So, again, these types of foundations are really specific to what are the conditions of the site. Right? What kinds of soils do I have? Right? Or what kinds of soil do I have to go through? Right? If you had clay on the top, that's great. Right? But if we continue to drill down and we hit a layer of sand, that's problematic. Right? So we have to be very careful with what's happening, which is why those test bores are important, so we understand. Right? So, socketed caissons, right? Instead of just drilling down to a subsurface material that can actually bear the required weight, right? Ideally, you're drilling down until you hit bedrock, right? In a socketed caisson, instead of flaring out, right, you're actually continuing to drill into that material, right? You drill through. So instead of resting on, you're actually drilling into the material and giving you more bearing capacity. Because not only, right, are you bearing on the end, right, but the friction on the sides of that material, the bond between the concrete and the friction of the sides of the material, right? So the concrete and, say, the rock, if you're drilling into bedrock, right, gives you more ability to bear more weight because you have that friction that's holding it as well, right? So not only is it end-bearing, but it's friction as well, right? So this can bear more weight than a regular caisson. Does that make sense? Nods? Yeah? Okay. Just making sure, right? Okay. So what's the major difference between a caisson and a pile? Pile is driven. Exactly. Okay? So a pile is forcibly driven into the earth, right? A caisson is drilled and then poured with concrete. Okay? The best part about a pile, right, is you can use it in non-cohesive soils or cohesionless soils. Right? If I'm in sand, no problem. I can drive a pile. Right? If I'm in a combination of soils, I have some clay, but I have some sand, I can still drive the pile. Right? So it's a little bit more universal. Okay? The problem is they can't be as large. Right? Because they have to be driven. Okay? So a machine called a pile driver drives the piles into the ground with repeated blows of some kind of a mechanical hammer. Right? The last time I drove out Highway 4, they were actually doing this, right, on one of the exits. I don't remember which one, right? But you have a pile driver, basically, right? It can be something as simple as a crane that lifts something heavy, right, and then drops the heavy thing, right? It can be something that's actually pneumatically driven, right? So that this block gets driven down, right, instead of just relying on gravity. Depends on what you're trying to drive and how easy it is to drive, right? But it drives that piece down, okay? It's driven until the tip of the pile encounters firm resistance, right, from a suitable bearing strata, right, like bedrock or something like that, right? So you just keep driving it, okay? It could be dense sand, it could be gravel, it could be something like that, right? So that is an end-bearing pile, right? It has to be driven until it reaches something solid, okay? Right? A friction pile, on the other hand, right, is driven into a softer material, might be clay, might be sand, right, without encountering a firm, solid resting place, right? But the length of the side of that provides enough friction against the soil such that it can bear the weight that it needs to bear, right? So you don't have to drive it as far, which is a big advantage, right? This is obviously for lighter weight buildings, right? It develops that load-bearing capacity simply because of the friction of the side surface of the pile and the dirt, right, so to speak, the soil. Okay? Piles tend to be driven closely together and then capped with what's called a pile cap, right, which distributes the concentrated load coming down, right, into a variety of piles. Okay? And so this is what I was talking about piles can't be that large. When we talked about caissons, they could be as large as 8 feet in diameter, right? That's a lot, right? We can put a lot of bearing on that one 8-foot piece. Piles tend to be much smaller, right? And so if we're talking about smaller things, we need more of them to support the same amount of weight, right? So this is exactly what happened for the new span of the Bay Bridge, right? We needed the ability to make a foundation, right? Obviously, it's in the middle of the bay, so there's water in the way, which would be probably the most cohesionless material we could be working with, right? We can't drill through the water and have an air hole, right? It's not possible. So we need something. We can't pour concrete. We need some way of driving, right, from the surface down. So we end up driving, in their case, it was precast concrete piles, right? We drive those down until they hit a suitable bearing, and I believe they're all end bearing, not friction piles, right? And then at the top, we pour a concrete cap that ties all of them together and lets them act as a unit rather than individuals. Okay? So they distribute that load to a variety of piles that are below. Okay? So we have a variety of pile caps here, right? Different examples depending on how much load we're bearing, how many piles are involved. Okay? So the thing about it is the more piles we have, right, the more stress they put on the soil itself, right? And so the amount of soil that's affected by it. So if we have one pile, it's a very small amount of soil, right? If we have 4 piles, it's a larger amount of soil. And if we have a bunch of piles, right, it affects a much larger piece of the soil, right? Particularly in friction piles, right? So it's just important to recognize that can cause major things, okay? So load-bearing walls that are on piles. This is where I said we'd come back to this, right? So this idea of the grade beam is a lot like a pile cap in that it transmits the load between a variety of piles. Okay, and so a grade beam, and again, the book only shows it on a hill, which is a total misnomer because it's used a lot in other contexts. So on a project that I was working on in Lafayette, classic clay basin, clay soil. We needed a way to support these buildings such that we wouldn't have differential settlement, right, which would cause the cracks and all the stuff that's historically in the 1960s buildings that are built, right, in downtown. This was for a multifamily 7-unit complex. And so we needed the ability to have a foundation so that the building could exist independent of that clay soil expanding and contracting, okay? So what we did is, and in this case, we didn't drive piles. We drilled very small caissons, right? And so I said the minimum size of a caisson was 18 inches. We had a few 18-inch piers. We had a lot of 12-inch piers. That was what the engineer specified. Again, it's only a 2-story building, right? So it wasn't too much weight. And so we drilled all those, and I think we put 105 cubic yards of concrete into the ground before we did any of the actual stem walls, which is an incredibly large amount of concrete for 7 units. But all of those, right, did exactly this. It was a flat lot, right? But we had these piers that were all tied together with beams, right? And so the piers, right, or the caissons, or the piles, in any case, right, were, right, using the friction of that against the soil to hold the building in place. Okay? So the top surface of the soil, that was all that nasty clay, could expand and contract independently of the friction that was actually holding the building up down deeper in the earth. Okay? And so when you put all of those together, you have a building that's incredibly, incredibly stable and consistent. And so we did this project, 15 years ago, so it's been a while. And if you go back in the building today, there's not a single crack in any of the doors. There's no settlement. It works as a complete unit, right, rather than any kind of differential settlement. And it's in a soil that is notorious for moving around, right? But these are consistent. So there are ways to get around it, which is what's important, right? And so I wanted to bring up the story to help illustrate this and why you might use something like this. Okay? And so an engineer is always going to be the one that's going to specify how much rebar, how big are the holes, how big are the piles, right? That kind of thing, right? But the concept is the same whether you drove the piles or whether you tied things or whether you drill them and then fill them, right? So this is a great beam, right? Different example. You don't have to draw it in your sketchbook. It's okay, right? You've already breaking you into drawing, right? So in this particular example, it looks an awful lot like the slab on grade that we talked about before. Right? You remember we kind of drew something like this? The difference is that this end here is acting as a beam. So the beam's running in this direction, right? Like this. It's resting on one pile here, right? There's another pile out here, and the beam is spanning between the two piles, right? And the piles are providing the support. The friction of the piles against the dirt is providing the support for the building above. Okay? So the slab isn't actually providing any of the bearing. Right? It's these piles. It's always hard to kind of see it in sections. Okay? So, if we're talking, yes? How does the slab attach to the pile? Good question. Did I go the wrong direction? There we go. Okay? So, typically, right, and we're not seeing it here, but I'm going to try to point it out on here, right? Typically, our pile or, right, our caisson that we poured, right, would have rebar reinforcing that comes out of the top. Okay, that rebar reinforcing, along with, depending on the specific design, a form of a key or a keyway, which is just a depression in the concrete, right, would serve to interlock this with what's happening up here. So you would drill, right, or drive your pile, right, on top of that pile, right, on top of the fresh concrete as it's curing, the rebar would be sticking out. You would then tie that rebar into the rebar that runs along the length of the beam, right? Build up your formwork on either side of the beam, and then pour the beam. Does that make sense? So you're tying that whole thing together. And when we get to concrete and site cast concrete and that sort of thing, I'll be able to show you more specific examples. So remember that question for about 2 weeks and ask me again, okay? And I'll show you more specific examples, because that's when we'll talk about it. Okay, so when we talk about piles, there's a variety of different kinds of piles, right? Wood would be the simplest to work with, right? And it was kind of the earliest form of a pile, okay? So it's limited in length, right, by the size of the tree that you cut it from, right? So however large the tree is how big the pile can actually be. In terms of bearing capacity of one of these, we're talking about 10 to 55 tons, okay? The big problem is, right, they're subject to decay, right? How many people have been to Venice, right? How many people have experienced the fact that Venice floods, right? Okay, or at least are aware of it, okay? So Venice is a great example. Venice is built on wood piles, okay? So pretty cool idea, right? We need to build our city, right? We need some kind of a bearing capacity. So we drive these wooden piles, right? We build our city on top of it, right? And we've got these really cool canals, and it's, you know, romantic and all that kind of stuff when you go with your wife and whatever, right? Girlfriend, even better, right? So you do. You guys finally caught on to that, right? Jeez. No, so you're in this great place, right? But the problem is they're all built out of wood, right? And that wood has a limited lifespan. And certainly when wood is underwater, it tends to last a lot longer than if it's exposed to the air. Okay? The problem in Venice, right, is that not all of that wood is underwater all the time. Right? You've got things like tides that go up and down. Right? So a lot of these pieces, a lot of these wood piles are slowly starting to decay. Right? The other factor is that we put a bunch of really heavy stone buildings on top of these wood piles. Right? And so over time, over hundreds and hundreds and hundreds of years, the whole city is sinking. Right? And that's why we're starting to get more and more flooding. Right? So that's the extreme example of piles, but it's a good one. Right? And specifically wood piles. Okay? So what have we done to combat that? Right? We've moved into the realm of steel piles or concrete piles. Right? And if we were to retrofit part of Venice, we would use one of these. Okay? So steel piles, the great thing is that they can be welded together to basically become an infinite length piece. Right? So unlike trees, which are limited to how large was the tree, right, to make the wood pile in the first place, steel can be almost infinite, right? Because we can bring a piece, drive it, weld on a new piece, keep driving it, right? Which is a big advantage, okay? Generally, we're going to use round, right, which would be like pipes, right, or H-section or wide flange, right, which would be like the ones that are shown in this picture, right? They're going to be somewhere in the neighborhood of 8 to 14 inches in diameter or rough size, right? The H piles are a big advantage because they don't displace too much soil when driven, right? So when you're driving them, they don't create a mushroom at the top with displaced soil, which is called heaving. And so that can be a good advantage, right? If you're doing one of the round ones, you have more tendency for this heaving. And they can bear somewhere between 30 and 225 tons of bearing capacity, right? So much higher than the wood columns, right? Now, what would be some of the disadvantages of steel? What was it? Cost, sure. Corrosion, right? So if we were to say, guess what? We need to retrofit Venice, right? Yeah, what a big deal, you know. We need to retrofit it. We're going to use steel piles. What would we be concerned with? Corrosion, salt water, right? Those kinds of issues. So that's a big problem, right? If we were going to drive piles for the New Bay Bridge, would we want to use steel? Probably not. Same issues, right? So steel's great in a place where it's not in contact with things that cause it to corrode, right? So what have we come up with to combat that? Okay, we come up with precast concrete piles, right? And so this is, if you've ever driven on 680 or out Highway 4, you've probably seen the weird truck, right, that has like the cab of the truck, and then there's this big, long concrete beam-looking thing and a little trailer at the end that's holding up the end, right? You guys ever seen this driving along? Okay. If you pay attention now, you will probably see one because they're very common in the Bay Area. The reason they're on those two freeways is because the plant that makes them is in Oakley, right? So you see a lot of them, okay? In cross-section, they can be square, they can be octagonal, they can be round, right? Depends on the facilities that's making them. Most commonly, they're square, but it varies a little bit, right? They're manufactured, right, in advance on a particular site. That's why they're precast, right? Then they're carried to the site itself, right? That has limits in terms of how long they can be, right? So one of these precast places, which we will talk about, I have videos of this process and how they make them, and we'll do that in 3 lectures. We'll talk about this, right? But you have to be able to get these, right? You can make them almost as long as you have formwork to make them, right? But you somehow have to get this to the site where you need it, right? So there are some limitations for how long they can be, right? You can't weld them together and make them longer. They have to be cast in one piece, right? They can be pre or post tension for maximum strength. If it doesn't make sense what those two things mean, then we'll talk about it in 3 weeks. I don't want to overload you right now, right? They're 10 to 16 inches in diameter, right? So we're talking, somewhere between here and there, right? And they have 45 to 500 ton bearing capacity, right? So these are definitely the strongest in terms of what they can bear, right? And they're also corrosion resistant, right? We can put them in salt water. We can use them for the Bay Bridge, right? That's a really good use of them. Yes?
The salt doesn't affect the steel rebar inside?
Great question. So if we're going to, and we will talk about this when we get to reinforcing anyway, but if we were going to put this in an environment where they could potentially be in contact with salt water, we would use one of two things. One, we'd use either stainless steel rebar, right, which is resistant naturally by its process of being made, or we'd use epoxy coated. We wouldn't use zinc because it reacts with the concrete, but we'd use epoxy coated. I have examples of these which I'll pass around. See if I can grab them really fast. Of course, wouldn't you know they're not? This drawer is getting full of these. Here's a stainless one. Ah, I do have them. Since you're asking, right? So this is a piece of stainless. All right, these will go around again, right? So this is corrosion resistance because it's stainless steel. This one, it's green. If you've ever seen a purple piece of rebar, like on a freeway or something, same kind of thing. It has an epoxy plastic coating on it that resists that kind of corrosion, right? Today's not a big touchy-feely day because there's not that many things for me to pass around, but there will be days where there's lots of stuff for you to actually see. Yes, Casey? Yes. No, because it's really difficult to attach those two pieces, and they would lose their bearing capacity through that attachment point, right? And so they need to cast those in one monolithic piece for them to work correctly, right? So if you needed a pile that was too long, you'd have to use steel, right? And so in a precast facility, the casting beds tend to be about 800 feet long. So theoretically, you could make an 800-foot pile. The problem is getting it from that facility to wherever you were going to drive it, and then how on earth do you drive this 800-foot thing, right? So generally, they're in some reasonable length, right? I'd say up to about 100 feet, right, depending on what you're doing. Somebody else, you had a question.
I was going to ask if they ever had to do on-site precasting for those.
I've never heard of it. The problem would be having the facilities to do it, and a lot of times they're very specific, and I'll show you the videos of kind of how it works. But the casting beds and the facilities for how they run and pre-tension the piles, and then the steam curing process that they go through, it would be difficult to transport that stuff to a site to actually do it. So I've never heard of it, but it doesn't mean it's out of the question, right? Depends on the specific location, right? So we also have what are called cased piles, right? These can be site cast, right? And the idea here is that we drive a hollow steel shell into the ground, right? Once we've done that, we fill that steel shell with concrete, okay? Which is kind of it's a hybrid. It might get us there. It's not quite as good as a precast concrete in terms of corrosion resistance, but it does give us a little bit more flexibility, right? 45 to 150 ton bearing capacity, right? And again, I'm not going to ask you a true or false question. Do cased piles have a 45 to 150 ton? I'm just trying to give you these numbers as an order of magnitude, right? So you would understand that a precast concrete pile can bear the most weight of all of them. Does that make sense? Yeah? Okay. The other thing that we have are what are called uncased piles. These are not particularly common, but there are a variety of proprietary techniques for doing this, depending on who the manufacturer is and who the contractor is, right? They're basically pressure injecting concrete using a proprietary system to make a pile, right, in the process. It's kind of a weird one. You can look through the book at some of these examples. You can Google it to get some examples. But basically, they're driving this steel shell in, and then they're pushing the concrete through this steel shell, right, down into the ground where it makes the pile, right, and then they remove the steel off the top of it, right? It's kind of a weird proprietary thing, but it's important for you to at least be aware that it exists, right? So, if we're in significant earthquake zone, sometimes we have to think of creative ways of helping our buildings withstand earthquakes, right? And so there's a variety of strategies for how we might do that. We'll talk about those as we go through the various types of buildings, right, and what we must do. But one of the things that's important to understand, since we're talking specifically about foundations, is that there is a way of helping a building to survive an earthquake, right, by actually putting the earthquake on these little flexible seismic base isolators, right? And so the best example of this, and it's specific, it's for a specific case, and I'll illustrate this specific case right now. So UC Berkeley is built on a fault line, right? You guys are aware of that, right? Many of you may know that the stadium is actually right on top of the fault, and for a long time, half the stadium was moving one way and half the stadium was moving the other way, right? I think it was getting like an inch longer a year or something, right? Kind of creepy, right? But there's a variety, not just the stadium, there's a variety of other buildings that are right on the fault as well, okay? The most notable of which is the Hearst Mining Building, right, which is built basically right on the fault. It's considered to be a very historic building. It's actually a beautiful building, right? Built out of stone, cut granite blocks, and it's just really exquisite building. Okay. It was, however, since it was built on the fault, right, at risk of collapsing during an earthquake. Right? If it's built out of stone, it's lots of individual pieces. Those can crumble during an earthquake. That's kind of a big problem. Okay. The thing about it is, since it's built right on top of the fault, right? If an earthquake were to hit, this particular building would get a big jolt at once rather than a rolling, undulating earthquake that would be once the earthquake spreads out, right? So if they could take the building, right, and allow the building to absorb as a unit that one big jolt, right, the building could actually stay intact rather than crumbling into a bunch of pieces, right? So what they did is they dug down under the building, right, poured an entirely new foundation, right? And then on top of this foundation, they put these seismic base isolators, okay? And basically the concept here is you have a plate at the bottom, right? You have a sandwiched layer of steel and rubber, right, that run in between, right, here and here. Then we end up with a top base plate that attaches to the building, right? Or attaches to the former foundation of the building, depending on how you generate this. And what it allows you to do is when the building is sitting stationary, it's perfectly fine, right? But then these isolators, if an earthquake were to happen, would allow the building to move up to a foot in either direction when the earthquake hit, right? I've heard of skyscrapers having these and being able to move up to 3 feet, right? So depending on the scale of the building, you're going to move more or less, right? But it's keeping the building together as a unit rather than letting that force ripple through the building and cause it to collapse, right? So it's a very distinct strategy. It was actually developed at Berkeley, right, and is now being used throughout the world as one of these ways of addressing earthquake issues. Yes? It corrects itself after the earthquake. So it moves and absorbs the force, right, rather than causing the force to cause the destruction in the building itself. Because it needs that, right, here to be able to absorb that force, right? If we had something too hard here, it would be too rigid, right, and wouldn't allow us to absorb the force. Does that make sense? Right. It's the rubber part that brings it back, right? So it's the combination of the whole unit. And I'm not an engineer, so I don't know the exact makeup of how it works precisely. But the concept is that it's designed around the flexibility to move and then return to where it should be, right? So anyway, that's one of the ways we've developed to combat earthquakes, right? And of course, we're in California. It's impossible not to bring up earthquakes throughout the building process. So we will certainly cover earthquakes in more detail as we go along through the class, okay? So starting with one last little topic, right, still relevant, retaining walls, right? A lot of people, if you're built on a hillside around here, there's a lot of hills, have retaining walls, right? There's 3 reasons why retaining walls fail. Can anybody give us one of them? Yeah. Okay. Erosion, kind of. Yeah. The load from the hill behind it. Okay. So we've got overturning, right? The load from the hill behind it, right? Pushing it over, right? We've got undermining, right? Sliding out from underneath, right? And we've got sliding, right? Which is nice and even, but it's still not holding the dirt where we want it to hold, right? And so what do we do to combat that, right? And so we've got a variety of different options depending on our excavation types, right? In this particular example, right, we have a tapered retaining wall, right, which helps. We have a nice footing at the bottom. Remember when we talked about footing, right, that when you load this, right, it wants to overturn that way, right? Remember that when we talked about that on a footing, right? In this case, it's a good thing, because we've got a bunch of stuff pushing it back that way. Right? A bunch of weight from the hill pushing it back that way. So we get the benefit of the fact that it wants to overturn, all right, helping us to hold the hill back. All right? Another example here, this is a T-type, right? In this particular example, the disadvantage would be that we'd have to excavate back much further to be able to pour this, right? But the advantage would be the dirt is resting on the top of this footing, which isn't allowing it to overturn, right? Because the dirt's also pressing down as it's pushing out, right? But bigger excavation, which is problematic, right? Cantilever type, right? Very similar to the T-type. It's just slightly off-center, right? But it's basically the same concept. Obviously, inside of each one of these, there would be a large amount of rebar and steel that would help this to work, which we'll talk about down the road. And the last type is mass, right? And that is the idea that we build a wall that's heavy enough so that it can't overturn, right? And it can't slide because it's so heavy, right? And so this was kind of the old-fashioned way of building a retaining wall. You build it big, tapered, and it doesn't overturn, okay? So we have to move from that, right, into the idea that water can somehow percolate into these foundations, and we have to deal with water. Water is always a problem, right? And so in this particular case, right, this is with a basement inside, right? There are a variety of ways of trying to drain out water, right? Because water's naturally going to try to come in, okay? So something like this, right? This was our original excavation. By the way, given this angle of repose, what kind of clay, what kind of soil would it be? I just said what it was. It's cohesive soil, right? It would be clay, something like that, right? So we have this. We cut this down. We put in our footing. We put in our wall, right? When we go to backfill, right, we put a drain pipe in first, right, followed by, right, a bunch of rock supplemented with the backfill, right, and we get to the top, it's more of just the soil itself. The idea here is that as water comes in here, it reaches this much more porous material, and instead of running up against the house, right, it drains down into that drain pipe, which we can then get rid of. Make sense? Right? The other option that we have is we can use a drainage mat, and there's actually one in the back here. It's not the one that's pictured, but it's very close to it. Right? Something a lot like this, right, which I'll pass around. It's a plastic material, right, that would go up against, and I'll pass this around so you can see it, right, that would go up against the wall, that would allow when water comes against it, right, water would then enter one of the cavities that's in it, which you'll be able to see, and drain down to the drain, right, which allows us not to put as much rock, right, we can just do regular backfill. That's why it's coated in this filter fabric, right, to keep the fine dirt particles and stuff out, right. So that's just a different example for how we're keeping that away from the building itself. Yes? We haven't gotten to the membrane yet. It's coming. What? Yeah? Yes. Backfill's just the soil that was removed previously. Okay? So these are a little bit smaller examples, right? But the idea here is that if we have a deeper foundation, we have to get the water that's collected in those pipes out, right? So in this particular example, the slab is above, and we have this little sump with a place where we can pump the water out, right? The other example here, right, is that we have this sump, right? This is a foundation mat. It's a slightly different foundation type, but we didn't really get into that, right? The slab that you're actually inhabiting is much higher, right, which is then getting the drainage out that way. And I think the next one is the waterproofing that we're going to talk about in more depth, okay? So yes, the sump in this case would be permanent, right? Now, if you have a building where you can naturally collect that water, let's say your building's on a hillside, right? If you can collect the water at the back, right, and pipe around the house out to the front where it can naturally drain, then you don't have to have a sump, right? If you're in an area where you're digging down and you have soil on all sides, then you have to basically pump. You don't really have an option, right? So it depends on where you are to some extent. Okay, so this is bringing up what you were just talking about. That's good. I'm glad you were there, right? This drainage mat by itself isn't enough to get rid of the water, right? Concrete has some porosity to it. It will allow water to come through it. If that's the case, we need to do something where we're actually going to waterproof or create a waterproof membrane between, right, that mat and the concrete to not allow the water to come through. Okay? There's two different types that we can use. The first is a liquid, right? Some of you might have worked with similar products like the Henry's like black goo that you can use and whatever. The idea here is it's a paintable substance, right, that comes in a liquid form, solidifies into kind of a waterproof gel layer type thing, right? It's kind of like an epoxy paint sort of thing, right? Or it could come in a sheet good, right? The best example is the bitutain type sheet good, which is also used in roofing, right? But the idea is that it's a sheet good that has a sticky side, and you glue it onto the foundation that way, right? And there's advantages to each. The liquid is easy to install, right? Especially if you have complex areas, you have pipes or something weird coming out. It's easier to just paint on a liquid, right, than to try to cut a sheet good around that, right? The disadvantage of that is that it can go on very uneven, right? You're just painting it on. It might be thicker in one area, thinner in another area, which is more risky, right? Sheets are perfectly even. They're the same thickness all the way along, but it's hard if you're trying to cut around some kind of odd-shaped object, right? So you have to be aware of the differences and why you might use. A lot of times you use a combination of both, right, depending on what you're trying to cover, right? So this dark black area in this particular drawing is that waterproof membrane, right? This is a little bit more complicated because we have a concrete block wall with a brick facade, a brick veneer, right? So we have the waterproof membrane further inside the building, right, than it would necessarily be depending on the type of building, right? But then it runs down the foundation, and in this case it's running down to the drain and also running along here so that we can have another set, right, before we put the slab on. So it's a little bit more complicated, but you get the idea, right? This is, right, back to this slide, okay? But when you draw this, I want you to add some notes, so I'll draw with you, right? You could choose which one you want to draw. Okay, so I'm going to draw this foundation wall here down to my footing, right? And I have my inside. This would be my inside, so we'll draw my slab over here, right? And I'll make a note that this is inside, right? Inside, okay? Doesn't hurt, right? Since we're still doing this, I'll call this a footing, slab, right? Always good to put extra notes on, right? But what I'm really concerned with, right, is my two different options, okay? And so I'm going to pick the one on the right with the perforated drain mat, right? But it's up to you, okay? And so we'll draw this mat in. Make sure I do it correctly. We'll draw it like that, right? And I'll label this as perforated drain mat, right? Down at the bottom here, right, I'll have my drain pipe. Right? I'll have my excavation, right? And so we'll call this excavation, right? And then, right, in this region I would have my backfill. The hatch for a backfill is generally this on an angle, right? This is what blueprint reading classes are for, right? You don't have to know this. I'm just doing it, right? And if I was doing the hatch for regular dirt, it would be orthogonal, something like that, right? And so I'll call this backfill. Right? And then the last thing that I want to do is I want to make a note, and it's not shown on here, right? But I want to make a note and make a nice bold line that's something like this, right? And I'm going to call this waterproof. Here, let's move this down here, right? We'll call this waterproof membrane. Right? Make sense? Right? The other option, if I was drawing the other one, right, is I would draw in the crushed stone. right? And I would label that crushed stone. Make sense? Right? I've seen it done where they put the drainage rock in anyway. The truth is that depending on what soil you have, where's that sample passing around? Did it stick back in the drawer? Do you mind? So, depending on what soil you have, right? If you have too fine a soil, you're going to clog this, and it's not really going to serve its purpose. So, a lot of times, in order to prevent this from getting clogged, the fabric that's on here, right, the filter fabric, they'll go ahead and put this crushed stone in front of the drainage mat, right, to make sure that not all of the dirt is right up against this, clogging it up, not having it work, right? So it's very common to have the actual crushed stone as well, right? That, depending on which drainage mat you pick, it might not be required. So. Okay, so this is just the Francis Ching version of it, right? But it's virtually the same thing. I'm not asking you to draw it, right? It has a little bit more detail, but I like to have it as reference so when you go back and look at the slides, right, you can kind of understand. One of the neat things about this class is I'm showing you a bunch of examples of foundations today, and you don't necessarily understand everything that's happening. You don't understand what's happening above and whatever yet, right? But by the end of this class, you'll be able to look at this, and this same drawing will mean a lot more to you, right? And so that's one of the cool things, and part of why I'm showing you the fully technical drawings now, right, as opposed to waiting. Okay, so that's it for today. You get out of here 10 minutes early, which is good, right? Remember to read chapter 13